So, we established in the last section that if you want to take the sum of infinitely many terms, then what that actually means is that you are going to take a partial sum, namely the sum of the first, say, big N terms, and then take the limit as big N approaches infinity. So in practice, actually computing the infinite sum, the infinite series is what we're calling this, actually computing this thing is reliant upon being able to obtain a formula for the partial sums. being able to obtain a formula for this bit right here. And in almost every case, that is going to be either impossible or close to impossible. So we looked at a couple cases in the last section where we were able to do it. With geometric series, we were able to do it. And with telescoping series, we were able to do it. But there really aren't any other examples that come to mind where it'll be very easy to find a formula for the partial sums. So, moving forward, we are going to move away from the question of determining what the sum actually is, and instead, we're just going to ask whether this guy converges or not. So does this sum even exist in the first place, or does it explode to infinity, or does it just oscillate forever? So this section and the next few sections are going to be dedicated entirely to tests for determining whether a given series is going to converge or not. We've already seen one of these tests, namely the divergence test. So if the limit as n goes to infinity of the terms of the series do not go to 0, then that means the sum has to diverge. So that's one test already under our belt. Now we're going to include another one called the integral test. So, if you want to write these partial sums in a more succinct notation, then you might use the big sigma here. So here we're going from 1 to big N. So here we're going from 1 to big N. That's what that notation means. Now notice this is very similar to the definition of an improper integral. So here we have a sum from 1 to infinity. Here we have an integral from 1 to infinity. And an integral is sort of like a sum. And we define this integral in very much the same way that we defined this dude, namely by taking a finite sum, or in this case a finite integral, and then taking the limit as the upper limit goes to infinity. So, based at least on the similarity of these two definitions, it is reasonable to suspect that if the terms of this series are given by a function, where this function can be anti-differentiated, then maybe information about this improper integral can give us information about this series. And indeed, that's what the integral test is about. It's we want to compute an improper integral and have that give us some information about the series. Okay, so let's look at a specific example. Let's look at f of x equals 1 over x squared. And we're going to look at this geometrically. So in particular, if we take the series where the terms are given by 1 over x squared, so 1 over n squared in this case, we can interpret each of these terms as being the area of a rectangle. So 1 over n squared, well, that's the area of a rectangle where the base has length 1 and the height is 1 over n squared, right? Because the area of a rectangle is just length times base, so 1 times 1 over n squared. So let's take a look at what all of those rectangles are going to look like. Because if each of these terms represents the area of a rectangle, then the infinite sum represents the area that you would get upon adding up the areas of all those rectangles. So let's move over to Geogebra. So here we go. So here is the curve 1 over x squared. I have only focused on values of x from 1 to infinity, because those are the only numbers that's going to interact with our series. And then here, this first integral, so it has a base of length 1, and it has a height of, well, it's touching the curve. So if this is 1 over x squared, then this is at 1 over 1 squared, so 1. So this rectangle is the first term of the series. Okay, what about the second rectangle? Again, the base is 1, and now the height is at the function at 2. So the height is 1 over 2 squared, or 1/4. So 1 times 1/4. So this area represents the second term in the series. Similarly, here we have a base of 1. We have a height of 1 over 3 squared. So this is the third term of the series. This is the fourth term of the series. And you can keep on going forever. So notice that because this function is decreasing, these rectangles are always overshooting the curve. These rectangles always lie above the curve. You know, there's this extra space between the curve and the rectangle. So that means that the value of the infinite series, which is what we would get if we were to add up all of these rectangles all the way off to infinity, that area is going to be greater than the area under the curve, because we have all of this excess. So that tells us that the infinite series is going to be larger than the improper integral, because the improper integral gives us the area under the curve. So indeed, that's what I've written here. If we look at things geometrically, it is not too hard to conclude that the value of this series, which does exist, by the way, I think we determined that last time. Or, no, not the series, the integral. The integral exists. This was an example, I think, that we did in the improper integrals section. But in any case, yeah, the series is larger than the improper integral, and we got that fact by looking at areas. So think about what that actually means, though. If the integral diverges, right, suppose that this wasn't 1 over x squared, but it was some other function. If this integral diverges, so it explodes to infinity, then this integral, or this series, would also have to diverge, because it would be larger than infinity, so infinity itself. So if the integral diverges, the series must diverge as well. On the other hand, look at what happens if we remove just one term of this series, and then move everything over to the left. Okay, so what I'm going to do is I'm going to remove this big rectangle, and then I'm going to take everything else and just shift it to the left by 1 unit. Okay, that's what I've done there. So I've removed the first rectangle, and then I've taken everything else and just shifted it over to the left. So now, if we add up the areas of all of these rectangles, we are getting still the infinite series, but with the first term missing. Now, just removing the first term isn't going to change whether the series converges or not. So if all we're interested in is convergence, then this is fine. But what we see here is that just by removing that first rectangle, now all of these rectangles lie beneath the curve. So that means that the series, with the first term removed, is actually going to be smaller than the improper integral, because now everything lies beneath the curve. So indeed, this is the second observation that I've made here. If we take the sum from n equals 2 to infinity, instead of n equals 1 to infinity, then all of a sudden we get something which is smaller than the improper integral. Now think about what this means. If the series diverges, if this series diverges, then that means that the integral must also diverge. And if the integral converges, then that means this series must converge, right? If the integral converges, then that means it's finite, which means that this series has no choice but to be finite as well. And then if this guy converges, well, then we can just add on that additional term, and that makes no difference. So, what do we conclude from this? Well, the reason that this worked, the reason that we got these two inequalities, was specifically because this function that we were using was both positive and decreasing. So if we want to generalize this result, we have to mention that. So this is the integral test. Suppose that a function is continuous on some interval, and it is positive and decreasing on some other interval. So notice it doesn't have to be always positive and decreasing, it just has to be eventually positive and decreasing. Because if it's like oscillating and doing wild stuff for the first, I don't know, billion terms, who cares? Just chop it off and throw it away. Convergence only matters, or convergence only depends upon what's happening in the limit as you go to infinity. So you can chop off the first billion terms, and that's not going to affect convergence. It'll affect the number it converges to, but we're not talking about that. So if this function is eventually positive and decreasing, then if the improper integral converges, the series also converges. If the improper integral diverges, then the series diverges. So it's easy. It basically takes the question of determining whether the series converges or not, and instead you just ask yourself whether the corresponding integral converges or not. And then, provided this function is continuous, positive, and eventually decreasing, those two behaviors will be commensurate. Okay, so test this particular series for convergence or divergence. All right, so we have to note that it satisfies the premises of the integral test. Is it continuous? Well, certainly. Pretty much everything we look at is going to be continuous. Is it positive? Certainly. N is taken to be a positive number, and n squared plus 1 is still positive. Reciprocal of a positive number is still positive, so no problem there. Is it decreasing? Yes, absolutely. Because the denominator, n squared plus 1, is increasing, but then we take the reciprocal. So the reciprocal of an increasing function is decreasing. So if we're going to use the integral test, then we do need to mention that the premises are satisfied. So clearly, this function is continuous and positive, and it is decreasing because it is the reciprocal of the increasing function n squared plus 1. So the integral test is justified. Okay, so if the integral test is going to work, then what do we need to do? Well, we just need to take the improper integral from 1 to infinity of this dude. Right? So what is this? So what's the antiderivative of 1 over x squared plus 1? Well, that's just the arctangent, right? So evaluate that between infinity and 1. So arctangent at infinity. So what is the limit of the arctangent as x goes to infinity? Well, that is pi over 2. Right? That was just look up our section on inverse trig functions. The limit of the arctan as x goes to infinity is pi over 2. And then arctan at 1. So here, let me do this. So that's pi over 2. And then arctan at 1. So that is going to be the angle between negative pi over 2 and pi over 2, whose tangent is 1. So break out your unit circle, or better yet, just memorize this fact. So the arctan of 1 is pi over 4. So it doesn't really matter what this number is. The fact is, it's a number. So that means that the integral converges. So pi over 4 is our final answer. But yeah, this number doesn't really matter. The fact is the integral converges, so that means the series converges as well. So the series, this dude, converges as well. Okay, so as an immediate consequence of the integral test, we have the so-called P-series test. So remember, when we were doing our section on improper integrals, we had this result that the integral from 1 to infinity of 1 over x to the p converges if p is larger than 1 and diverges if p is less than or equal to 1. Okay, well, now that we have the integral test, we can say exactly the same thing, but with a series instead of an improper integral. So this is worth remembering, certainly. So this series, 1 over n to the p, converges if p is larger than 1, diverges if p is smaller or equal to 1. So that should make testing some series really, really easy. Because now, just at a glance, we can say that this guy, for instance, 1 over n cubed, converges, because 3 is larger than 1, whereas this guy diverges, because the exponent here is 1/3, and 1/3 is smaller than 1. So the first series satisfies p equals 3, which is larger than 1, so it converges by the P-series test. The second series satisfies p equals 1/3, which is indeed less than or equal to 1, so it diverges by the P-series test. So this is definitely worth memorizing right now, because yeah, it makes certain problems just completely trivial. Okay, determine whether this guy converges or diverges, log n over n. Well, I mean, we pretty much have no, I mean, it's certainly not a P-series because we've got that natural log in there. So really, we have no other recourse but to try using the integral test. But in order for the integral test to work, we have to verify that the premises are satisfied. So, first off, what are the premises of the integral test? Continuous. Is this continuous? Well, yes, provided we stay away from 0, because log of 0 is a problem, and dividing by 0 is a problem. But we're starting at n equals 1, and we're only getting larger from there, so that's no problem here. And it is positive as well, because natural log is negative if it's between 0 and 1, but natural log is positive for everything greater than 1. And same deal with the denominator. So clearly this is continuous and positive for n greater than or equal to 1. Is this decreasing, though? Right, because that's the other premise. It needs to be eventually decreasing. That's not as obvious to me. So, to check to see whether this is decreasing or not, what we can do is we can take the first derivative and then show that the first derivative is negative. Because if the derivative is negative, then that means it's decreasing. And I should say eventually, because it only needs to be eventually decreasing. So to show that it's eventually decreasing, show that the first derivative is eventually negative. Okay, so I'm replacing n with x because if we're going to differentiate it, then we need the domain to be real numbers as opposed to integers. But, I mean, whatever, that doesn't really matter. So we're going to have to use the quotient rule here. So low d high minus high d low over low squared. So x over x cancels. Okay, so is this eventually negative? Yeah, certainly. Because the denominator is always positive, whereas the numerator, well, when x gets big, natural log also gets big, so 1 minus a big number is certainly negative. So negative on top of positive is negative. Okay, so the premises of the integral test are satisfied. So now all we need to do is just compute the integral and see whether that converges or diverges. This integral, to be precise. So how do we deal with this? Well, let's do a u substitution. Usually when you have an integral that has just a big natural log in there, a u substitution might clear things up. Well, I don't want to say all the time, because if it's like natural log, if it's like a product of natural log and something else, then you might need to use integration by parts. But for something like this, I mean, I've seen this example a million times already, so I just know that a u substitution is going to do it. Now we do have to be a bit careful here, because if we're doing a substitution, then that means the bounds of the integral are going to have to change. So when x is equal to 1, u is going to be the natural log of 1, which is 0. When x is equal to infinity, u is going to be natural log at infinity, and the limit of the natural log as x goes to infinity is infinity. Okay, so instead of 1 to infinity, the new bounds are going to be 0 to infinity. So now instead of natural log x, we have u. And then what is dx? Well, let's see. du is equal to 1 over x dx. So that means dx is equal to x du. So those two x's, these x's cancel out, conveniently enough. So we are just left over with the integral of u du, which becomes u squared over 2. Well, now we can see that this guy is in fact going to diverge, because what happens to u squared in the limit as u goes to infinity? Well, naturally that's going to explode. And then what happens when you plug in 0? Well, that's just 0. So infinity minus 0 is infinity. So the integral diverges, which means that the series, this series, also diverges by the integral test. Okay. So yeah, I mean, there's really not too much else to say about the integral test. I mean, ultimately, you're just taking the question of evaluating a series, and you're evaluating an integral instead. So, yeah, so the question is just being knocked back a couple sections into the question of integration. Yeah, really not much else to say about it. Just replace the sum with an integral and go from there. I suppose, the one thing that you have to be wary about is that the integral test is not always going to be applicable. It's only applicable if the terms of the series are eventually positive and decreasing, and also form a continuous function. So, like, for instance, if there was a factorial in here, then the integral test wouldn't be valid, because factorial is not a continuous function. It's only defined on the integers, so continuity doesn't even make sense in the situation. Okay, yeah, so to show that it is decreasing, the worst that it could be is that you might need to take a derivative and show that that derivative is negative, but I think that's as bad as it's going to get. Okay, so there is a little bit more that we can say about the integral test, though. Or not the test itself, but a consequence of the test. So, recall, in our initial discussion when we were talking about rectangles, we got these two inequalities, right? So this series is greater than or equal to this integral, and this integral, in turn, is larger than this series, with one of the terms missing. So, let's just take these two inequalities and push them together. Like so. Now, we can apply this argument recursively. Because here we have the sum starting at n equals 1. Here we have the sum starting at n equals 2. So let's just keep going, right? If the sum starting at n equals 1 is larger than the integral starting at 1, then the sum starting at n equals 2 is going to be larger than the integral at 2. So that's exactly what I've done here. I took this guy and I just did the argument again. Now, let's focus on these middle three terms here. These middle terms. Here, we have a series, and it is bounded on the left and on the right by improper integrals. Now, in general, we could have taken this chain of inequalities and keep it going as far to the left as possible, and at each step, the lower limit here is going to get bigger and bigger and bigger. So imagine that we just take this out as far as possible, out to some integer k. Well then, in general, we get this result. So the sum, starting at this arbitrary starting point, is bounded above by the integral and bounded below by another integral, where the lower bounds are themselves given in terms of this this new starting point. Now, notice the significance of this term in the middle here. Suppose that we wanted to approximate the infinite series by just adding up the first k terms, right? I mean, of course, we can just keep on adding terms forever, and we'll get a better and better approximation to the infinite sum. So let's say that we just added up the first k terms and then called it a day. It's a reasonable question to ask, how good of an approximation to the real sum is that going to be? Well, if we add up the first k terms, then the remaining terms are all of these, because here is the k plus 1th term, and then the k plus 2th term, k plus 3, all the way out to infinity. So this dude that we have here is the remainder. If we add up the first k terms, then this is the bit which is remaining. Hence, what we have actually done here is we have obtained an upper and a lower bound for the remainder. And that gives us a handle on the error in approximating this dude. So, this observation, it becomes the remainder estimate. So suppose that f is a function which satisfies the premises of the integral test. Suppose that this sum is convergent also. Let this guy be the remainder, or the error, upon approximating the sum with the kth partial sum. Right, so the kth partial sum is just the first of the sum of the first k terms. So the sum of all of the remaining terms then is the error in that approximation. So we're going to call that r sub k. Well, then this error is bounded above and below by these improper integrals, which hopefully we can compute. So that's good. If we can compute the top and the bottom, then we have a handle on the error. And consequently, we have a handle on how many terms we would need to add up in order to get a good approximation to the sum. So that is the idea here. Okay, so approximate the sum 1 over n cubed by using the sum of the first 10 terms. So add up the first 10 terms of this, and then we want to determine how close that is to the actual infinite sum by using these error bounds. Okay, so first off, let's go into Geogebra to actually compute this, because, adding up the first 10 terms, whatever, that's just arithmetic. So s sub 10, the 10th partial sum, is, let's see. So let's get rid of this. So you can do this in Geogebra really easily. So first, let's enter in our function. It is 1 over x cubed in this case. Then we type in sum, left parentheses, and then Geogebra helpfully fills in the sum notation. So we're going to go from 1 to 10. And then just enter in f of n like so. Now, for whatever stupid reason, it only does 1 decimal point by default, which, that's bad. We want more than that. So to get more decimal points, we go over here, and then down to settings, and then let's do 4 decimal places. So 1.1975. Okay. So now the question is, how close is this to the actual infinite sum? And in order to get an idea of that, we're going to estimate the error. Right? The error is the difference between the actual thing and the approximation. So to get the error, we need to compute these improper integrals here. So in this case, k is equal to 10. Yeah, okay, so whatever. Let's just go ahead and do it. I mean, this is x to the negative 11, so this is just the power rule. So negative and negative becomes plus, like so. Let's see. In the limit, as 1 over x squared goes to infinity, this becomes 0. So this first term is just 0. So 1 over 11 squared is about let's just leave it at that for now. So that's going to be the lower bound. As for the upper bound, k is 10 in this case. So once again, this just becomes 0 plus that. Okay. And I suppose if we wanted to put decimals to this, yeah. Oh, hang on, I'm being stupid, aren't I? Yep. Sorry, there has to be... Sorry, I did the power rule wrong. Ugh. So this is x to the negative 3, add 1 to get x to the negative 2, and then divide by negative 2. So there has to be a 2 here. Oops. Yeah, something felt wrong because yeah, strangely enough, when it comes to like reciprocals, I still mess up the power rule every now and again. I don't know why it doesn't stick in my head as easily as in the positive case. Okay. Okay. All right. So that's not too bad. That's not too bad. So the error, which is to say the difference between this and the true value, is guaranteed to be smaller than 0.005. So if you were only interested in like the first 2 digits of precision, then this would be an okay approximation. Now, for a more interesting question, how many terms would be required to ensure that the sum is accurate to within 0.0005? So we're putting in one more 0 here. So here we only took 10 terms of the sum. How many more would we need to take to increase the accuracy by an additional order of magnitude. Whale, in general, so in general, what does this integral look like? Because now it's asking us for what value of k is this dude going to have an additional 0 in it. So let's compute that improper integral in general. So that would be so plug in infinity, it goes to 0. Okay, so in general, this improper integral is 1 over 2k squared. So that's going to be the upper bound of the error. So we need, so to get the error smaller than this, so for what value of k right? Because r sub k, we want r sub k to be smaller than 0.0005. Now, because of the remainder estimate, we know that r sub k is going to be smaller than 1 over 2k squared. So, to get it smaller than 0.0005, we pick k such that the estimate is smaller than 0.0005. Yeah. So now all we need to do is solve this ladder inequality for k. So let's reciprocate both sides. If we reciprocate both sides, then that means the inequality flips. Divide both sides by k, or divide both sides by 2. That's positive, so that's not going to change the inequality. And then take square roots. Square root is an increasing function, so that's not going to change the inequality either. Okay, divide by 2, then take the square root. So what number is this? Uh, 31.6. About. So, because k has to be an integer, right? Because k represents the number of terms, let's just go ahead and round this up to the nearest integer, so 32. So we would need to take 32 terms to get the desired accuracy. Okay, so I don't have anything else to say about this one. For the most part, I think the PSeries test, this is definitely something that you have to memorize. Aside from that, I really think that the lasting lesson of this section is when you see a series and then the thing being added up is like weird, doesn't match any of the other convergence tests we're going to look at, then you do the integral test. The integral test is pretty much going to end up being our last resort for when nothing else is better. Yeah. All right. So that's it for this one.